Hello, this is Yichuan Zhao from Georgia State University. Today is my pleasure to give a talk in Bernoulli MS One Word Symposium 2020. Uh, Today I will talk about imperative for the bivariate survival function on the universal sensor. This is based on joint work with Haitao Huang from Georgia State University. The outline as follows. First, I talk about introduction, then talk about imperative for the bivariate survival function. Third one is a simulation study, and followed by that application to real data. Finally is a discussion. Bivariate survival data, this arise in biomedical study, financial and engineer application, etc. Particular example about the biomedical example is about prostate cancer data in Guo and Amita 2007 biometrics paper, particular Danish twins data and other data set. So the bivariate data include the univariate and the bivariate sensor schemes. In our paper, we discuss univariate sensor. Estimating the bivariate survival function can help us to predict the joint survival probability, assess dependence between the paired survival times, facilitate marginal analysis in survival analysis. About the non-parametric bivariate survival function estimator, special case is a univariate sensor. In that case, Lin and Yin 1993 proposed a non-parametric estimator for the survival function. In particular, we notice Dablaska in 1988 proposed that non-parametric estimator on the bivariate sensor. This is a natural extension from that one-dimensional carbon estimator to two-dimensional case. Follow the Dablaska work, there are many papers in the development. We consider the universal sensor case. This is particularly useful for the paired organ study on the same individual. So if you take a look at the notations, we can see bivariate failure times xi, yi, id with joint survival functions. Okay, s, xy, and the marginal survival function is s1, s2y. Univariate right sensor time ci, id with a survival function gt. We also assume that ci are independent of xi and y. The observed data are x tilde, y tilde, delta x, delta y, where xi tilde, xi minimum, ci, y tilde, and no censorship, delta x. This is the indicator function. Okay. Now, we are interested in that statistical inference for the bivariate survival function estimator in Lin and Yin and one with on the univariate right sensor. So Lin estimator based on the decomposition like this one, equation 1. So we estimated the corresponding expression h and g. Use h hat, okay, imperial survival function estimator of h. And also g hat is a Kaplan-Meier estimator of g based on and one-dimensional data set. Okay. Under that conditions, that estimator s hat xy, okay, is a uniform, strongly consistent, and has a weak convergence result as follows. Okay. So we can see for fixed xy, now s hat xy shares then asymptotic normality and follows. The variances delta sigma square like this one very complicated. So we need to have a good estimator for sigma square. Similarly, for one with estimator, we use a decomposition like equation 2. So g tilde xy, now you are the Kaplan-Meier estimators of g based on this data set. Okay. Now, similarly, that S tilde has similar statistical properties as follows. So the sigma tilde square has this form, very complicated. So we need to have a good estimator, but it's very difficult to give that estimator in that small sample. So the motivation as follows. So we need to give a beta into estimator because the normal approximation suffer from low coverage accuracies and may not preserve the natural range of the parameter, especially when the sample size is really small, the sensor is heavy, the shared data point is in the tail range. So motivate us use impure likelihood to develop that beta interval estimator. Okay, so we take a look at this. Okay, previous work over here, Lu and Burke 2008, and He, etc. 2016. Both their work have some limitation or may not cover this case. So this motivates us to develop new implant procedure to overcome the difficulty and also derive that chi-square distribution. So based on that decomposition, we have a WI. However, this WI not asymptotically ID. So this motivates us to get this ID decomposition. So the TI as follows, and also involve martingale. So over here, the parameters can be consistent estimator as follows. So we use UI denote this estimator. We just plug in MI and C for MIC and other parameters. So we have a UI asymptotic ID. So based on this, we have that impure likelihood ratio R theta. Okay. Use Lagrange multiply. So we have that lambda is a solution of this following equation. So the second one just give us that L theta 0 has that chi-square distribution when sample size goes to infinity. So use that, we can construct the confidence interval for theta. Okay. Similarly, for one width estimator, we have that ID decomposition T1I and T2I. Okay, like this one. Consider two cases. Now, based on this, okay, T1I and T2I. T2I. Now we take a look at, we use estimator, okay, plug in T1I and T2I, we have a VI, okay. So cover two cases, X larger than Y or X less than Y. So this by replace this parameter with this less than N estimator and carbon estimator, okay. So based on that ID decomposition, we derive that implicit ratio L tilde theta, then we'll consider holds for this proposed implicit method. It converges to the standard chi-square distribution. So this is a simulation study. Basically, we use the coupler models for the bivariate failure time. They have there are three cases. First, the independent coupler with univariate marginal distribution and the log normal marginal distribution. Second one is a Clayton coupler model. So with heterogeneous exponential marginal distribution. Third one is a Gumbel-Hogarth coupler with marginal Weber distribution. We chose different parameters. We can control this association between X, Y, and also control this sensor rate 20, 40, and 60%. Okay, and the sample size is 50 or 100, and repeat 10,000 times. Now we can compute the coverage probability and the average length of 95% coming interval by 4 methods, including the normal and the impure method. based on lean in and one with estimator. So we have three tables for the simulation study. Table 1, Table 2, Table 3 cover different sample size, cover different point XY, sensor rate 20, 40, 6%. So from these tables, we notice the result over here, Table 2, Table 3. Now we give a conclusion about the simulation study over here. So based on this, we can see in all cases, the interval by lean and one with imperative method have a better coverage probability and shorter image length than those by normal approximation counterpart, respectively. So compared to confidence interval by lean normal, confidence interval one with normal have a similar coverage probability and shorter image length. So especially on the heavy sensor. So in this case, imperative give us a better performance. So if we go back to that real data analysis, now we can see, take a look at over here. We notice this data, diabetic retinopathy data. One eye of each patient was randomly selected for treatment. Other eye was observed without treatment. Sensor rate 73 and 49% for treated and untreated eyes. So XY denote the time to blindness of treated eye in years. Okay, and also we have an age correlate and onset of a diabetic retinopathy. Classify the diabetic into two regional groups: young people and adult diabetic people. So involve sensor 68% and 55%. Okay, so this is the Bivariate survival probability plot. So this point-wise confidence interval. So based on this plot, and we have the following conclusion. So the purpose that imperative method just construct confidence interval for the Bivariate survival function on the universal sensor. The proposed method demonstrates superior performance over normal approximation in both simulation study and real data analysis. Okay. Okay. So this talk is based on a paper. The link of paper can be found in the following link. Thank you very much.